Greetings everyone and welcome back to the bench. Today on the bench I want to revisit the unbiased amplifier. If you remember a couple videos ago, I made this circuit and the output stage is unbiased, and I actually got it sounding pretty good. I was pretty impressed with the performance. But I want to increase the output power, and we have to take a look at a couple things before we can do that. I'm not going to get into how this circuit works. You just watch the previous video on that. So just to recap, I'm feeding the signal directly into the bases of these output transistors that are tied together. So these transistors cannot turn on until the voltage on their base reaches plus 6 volts for the upper transistor and minus 6 volt for the lower transistor. So there's that dead zone. So initially I had negative feedback coming off at this point, and when I did the demonstration it sounded awful. So then I moved the feedback to this point. What that does, the amplifier is feeding a corrective signal to the output stage to kind of make up for that dead zone. So it's trying to slew real fast to cover that dead zone. And it works. It makes the music sound much clearer. However, with music that has more pure tones, such as piano music, I can still hear kind of a buzz or a fuzz in the output from this amplifier. But it's really weak. I have to put my ear close to the speaker to hear it. So what I did next is add a resistor from the base to emitter, hoping that some of the current from the op amp is fed forward to the output stage, helping to fill in that notch a little bit, because there is still a little bit of a notch at the crossover point. In theory, the op amp should slew fast enough to correct that, but in reality, no op amp is going to be that fast, and there's still going to be a little bit of a notch. When I added that resistor in there, I could not hear that buzz anymore. It sounded very good. So now we have to deal with getting more output from this amplifier. And I also want to keep this circuit simple as possible. It's just going to be the op amp and the output transistors. You know, we're not going to have any drivers or voltage gain stages or anything like that. We're going to keep it simple. So we have to take a look at a few things. Well, because of our limitations here, we have to stay within the maximum voltage supply that the op amp can handle. Now, I know there's op amps out there that can handle more voltage, but I'm working with the LM4562 because it performs really well in the circuit. So a common operating voltage for the op amp would be plus 15 and minus 15 volts, or in single supply mode 30 volts. So I'm hoping I could get around 10 or 12 watts from this thing with a 4 ohm load. I don't have any idea. It all depends on if I have transistors with enough gain and the op amp can deliver enough current to these transistors to drive the waveform hard enough so I can get a full sine wave to the output with a 4 ohm load. So you might say, why don't you go with higher voltage here at the output stage, like plus minus 25 volts? Just use like Zener regulators for the op amp. Well, that won't work because your output swing is limited by the voltage that you're supplying the op amp. And remember, the emitter follower type stage doesn't have any voltage gain. So we're going to clip at the voltage that this op amp can put out. To make up for that would require a voltage gain stage, and again, I didn't want to complicate a very simple circuit by having that in there. So operating the circuit with higher supply voltages means there's going to be more current going through these transistors. So if I have a 4 ohm load here, we're going to have a peak current of a few amps, 3 or 4 amps. It'll depend on the reactance of the speaker and all that good stuff, but I need these transistors to have enough gain so that my limited drive current from this op amp can drive the transistors to be able to deliver that current to the speaker. Otherwise, our output swing will suffer and we won't get enough power that we're looking for. So the next thing was to get some transistors that would do the job. So I set up a little circuit here to test the gain of transistors at higher currents. So we're feeding in, like 15 volts here. And I used a 50 watt bulb here. And I used adjustable voltage here through a 100 ohm resistor. Adjusted the voltage, which in other words changes the current going through this resistor and into the base, to get about 3 amps here. So I wanted to find some transistors that gave me the most gain. And the ones I found were the FJP 5200 and FJP 1943 pairs. And I think the gain was around 80. And those are nice audio type transistors with flat gain across varying collector currents to a point. I mean, they still droop as the current gets really high. Plus, they're faster transistors. I just want to see how those perform rather than the MJE3055 and the complement 2955. Though those transistors will work okay in a pinch as well. Okay, here's the circuit. Really nothing to it. It's just the op amp and the output transistors. I have some supply decoupling caps. These are for the outputs and a couple for the op amp. Tried to lay it out so I can separate the power and the small signal ground currents. Can only do so much on these socket boards, so I don't expect perfect performance. If this amp works good enough, I might take it further and solder up a board and make a little stereo amp and do some tests on that. But yeah, I don't want to get to that stage just yet. So I made this little circuit here on the socket board. I did go back to plus and minus dual supply instead of single supply because it's just easier to set up on the board. And I'm just using one channel of the op amp. It's not stereo right now because I just don't have the room for that, and for testing purposes it's really not needed. Okay, we're powered up, plus or minus 15 volts. So I have the power supply set for serial operation. That allows me to do a positive and negative supply. Hooked up the caps. And I've been trying piano music. Stop, please. Okay. Been trying different resistors. The resistor that goes between the base and emitters right here. And also connected both speakers for a 4 ohm load because the lower impedance is harder to drive, of course, and get more of that buzz. So I've been trying different resistors and looking at 47 ohms. Yeah, I don't want to go lower than that. You can probably get away with 100, but 47 ohms seem to clear that any buzziness out. You just kind of have to listen and try the volume at very low to low levels and put your ear near the tweeter and just listen. See if that buzz is there or not. The kind of a fuzziness or buzziness to the sound. So I got rid of that. So what I'll do now is do a power test here. I'll put the resistive load up and get the scope going and see what kind of power this thing puts out. Okay, we're doing a power measurement test here. Oh great, this connection thing again. This oscilloscope probe thing is awful. Now we'll just have to see what we can do here. Nice symmetrical clipping. Let's tune that out. Put waveforms on the screen. 7.45 volts RMS squared divided by 4 is 13.8 watts. I'm kind of curious though. I'm wondering. Turn that up a bit. I just wonder. Kind of thinking that resistor's loading it down. Okay, remove that 47 ohm resistor, and I'm going to go up to 100. That might be our compromise. Okay. See, that didn't load it down as much. 8.58 volts. 8.58 squared divided by 4. 18.4 watts. There you go. And that's not too shabby at all. That's with 4 ohms. Let's see what we're getting with 8. So we'll adjust this up. Didn't change too much. It tells me we're not drawing too much current off the op amp. So we'll dial that out. Put waveforms on the screen. 9.07 volts RMS squared divided by 8. 10, about 10.3 watts. So not too shabby at all. Especially with 4 ohms, we're pushing about 18 watts. Well, I can tell by the difference in the power measurements there, though it's not double. The amp is not current starved because we're getting so much more with the 4 ohm load. Okay, let's zoom in here. I turned the signal down. And turn it down to about a volt or something. It doesn't really matter. Then we'll zoom in. I don't see a notch. Maybe just a little blip or something. Zoom way in. That's not a notch. That's just it triggering on, you know, a rising edge, and it's always going to be there in the center. So the noise is causing that. That's not a notch. There's no notch. Let's check at 10 kilohertz. Let's see here. Okay, now we're at 10 kilohertz. And I can see it. Yeah, there's a little... you can't really see it until you zoom in. There's a little notch. Let's see what happens when I pull that resistor out. See, it grows a little bit. Plug that back in. But, you know, that's so small, it's just not really going to be an issue at normal listening levels. And, of course, any harmonic at 10 kilohertz is going to be pretty much out of the hearing range. And it's so small, even if it did cause intermodulation distortion, it's so small, I just can't believe it would be audible. So matter of fact, let's take a look at the FFT here, see what kind of harmonics we're getting. Okay, this is distortion at 1 kilohertz. As usual, we have the 1 kilohertz fundamental, the 4.5 kilohertz pilot signal. That's 1% of this. And like I always say, it's just a reference. Like I said, it's at 1%, so it allows me to compare the distortion nodes. It's pretty clean, isn't it? Pretty clean. Not bad at all. But what I'm going to do now, and I saw a little second order node come up, but it comes and goes. But anyway, I'm going to turn the level down. See, now it's at a high level, close to clipping. But I want to check it at, let's say, 1 volt. And that's more of a normal listening level. To some of you will have it cranked all the way, but I would say 1 volt would be a good test. So I'll turn it down to 1 volt and come back. Okay, so now we're at 1 volt of output. And you can see we have a second order harmonic, which is jumping around 0.5 or 0.4, whatever it happens to be. And a couple, there's a third and a fourth, even a little fifth jumping around there. Kind of curious if it's due to the drive current here. Let me pull out this resistor. Pull that out. And that's not causing it. Because I know we were loading the chip down with the 47 ohm. And it doesn't seem to change. I think we might just be seeing, maybe it's this socket board. I'm not going to get great measurements here. It just could be the way the amplifier is, or it could be the layout with the socket board. And I might be able to do better if I soldered up a board, but this is still well under 1%. Okay, so now we're at 10 kilohertz, and I'm measuring at 1 volt RMS signal level. And of course I don't have a reference at 10 kilohertz because it would be at 45, which the music player wouldn't be able to reproduce. But knowing how high that was before, I can tell that it jumps around quite a bit, but nothing serious. There's some kind of jumps around, but there's some higher order that peak up. I wonder if I can set the scope. Let's see, maybe set this higher. Did that change it any? Stabilize those measurements any? Yeah, maybe it does. Or not, I don't know. But yeah, nothing serious, even at 10 kilohertz. Okay, we're looking at the square wave response of this thing. And it's at 10 kilohertz. And it's a really nice square wave. But if you zoom in, you can see that notch. I mean, that is a very fast rising edge. And you're not going to get rid of that. But, it's harmonics would be way out of the hearing range. But I was kind of curious if I put a capacitive load across the output, if it's stable or not. So let's do that. I'm putting a 0.01 microfarad from output to ground, if I can get it on there. And we're getting oscillation on the bottom. See that? It's oscillating. Minor oscillation on the bottom. And it's probably just this layout on the socket board. If I have this laid out properly with bypass caps near to the transistors, I'll probably eliminate that. So there you go. That's the unbiased amplifier with some more power. I mean, just listening to it, looking at the harmonics, it looks okay. Here's the complete schematic. This ended up being 100 ohms, and it works good with 4 ohm loads. And I'm showing the input filter and everything as a complete circuit. So the main concern for me is if this will be stable, because on the socket board I don't have some of the components, and like I said, the supply and the grounding is just not going to be ideal. The connections on those socket boards have some resistance, so it can make it oscillate. So I think the distortion we're seeing would be lower, and hopefully the oscillation, we might have to add some components to correct for that, but it might be okay if I solder up a board. And that's something I might consider pursuing in the future, because I think it's definitely a usable amp. But I'm going to wrap it up here, and I thank you for watching.